Okay, we're done with the transconductance amplifiers, and now we have filter applications. So this is going to be a short video because mostly I'm going to turn you guys loose. We want to create a filter that filters out 60 hertz ripple. It passes the frequencies lower than 60 hertz. And so we go through the equations and get this done. Design criteria. So now we're getting into designing. We don't know all the parameters exactly. What do you as a designer want to do? So they're going to place the corner frequency at 6 hertz, or 2 pi times 6 radians per second. And yes, it's a passive circuit, so we're going to choose the time constant to do that. Okay, 2 pi times 6, here's the 6 hertz right there. Okay. And the effect. This is the effect. That you have your signal, there's 60 hertz going in, 60 hertz, and what is 60 hertz going out? It's a spurious signal. It's what you don't want. It's stuff you don't want. That's the thing about it. So here's a circuit with a filter. So you're tuning it. We have an amplifier and tuning. Now, and it'll resonate at certain frequencies. You design it as a bandpass filter. Now, maximum gain at 91 megahertz. So of course that's, you design the omega for 91 megahertz. And you try to get that resistor as low as possible. Sometimes you can't help it. There's something going on. So you're told 2 components. You just got to find the capacitor. Anti-aliasing filter. When CDs are digital, but they output analog signals, you're digitizing an analog signal is what you're doing. And so any frequency components greater than half the sampling rate will be distorted. Ideally, it can be worse than that actually. So let's see what's going on. We want a low pass filter that passes stuff below this frequency, and this will be the we'll design right to this frequency. Omega is going to be equal to 2 pi times 22 point, the resonant frequency is going to be, here we go. It expresses it right there. You have to design things. You have to choose one thing and then find the other. So in this case, chose a capacitor of 1 nanofarad, and then, which is 1,000 picofarads, by the way, when you have to pick one out of a box. And you get this Bode plot. Two-stage filtering. So now you've got a steeper slope. You're filtering, but a second stage makes it steeper. 1 stage, 2 stage. End stages. You can make it steeper and steeper and steeper. But it gets a little crazy. Eugene Armstrong was a radio pioneer in 1919, World War I, and he had a 19-stage amplification of the radio signals, and he thought there's got to be a better way to do it. And he invented what's called heterodyning. So here's another filter to get rid of 60 cycle hum and the design. And this is capacitor, obviously, C up here. you're trying to get, so you can write everything down, what the output is compared to the input, and you have these equations to deal with it. And you want to design a notch frequency, so it's at 0 hertz it's 1, and it's going to be 1. You'll notice you got a 0 up here and a 0 down here. So you're going to have a double pole, which means you're going to fall off at 40 decibels per decade. And then you're going to have a single, a double 0 at 1 over root LC. Okay. Pick one, determine the other. Pick the capacitor, for example, determine the other stuff. And did not, let's see, it's going to start out at 1. I drew mine backwards, upside down. The impedance, yeah, I got it flipped. So band pass is when you choose the cutoff, one of the poles over here and 0 here. Band notch, we're choosing the pole here and then the 0 further up. There, get rid of my old one. Okay, here's an illustration of what aliasing is about. Here's a high frequency signal, and the big fat red one's a low frequency. But when you sample, you're sampling the points. You're sampling the same, you're getting the same point sampled. So when you reconstruct it, is it this red frequency, or is it is it 3 times higher frequency? You don't know. They presume it's the lower frequencies, which is why you can't, at 44 kilohertz, you can't sample faster frequencies. Okay. All useful frequencies are properly sampled. So everything you're interested in is sampled. That's the idea of this. Okay. Bass boost. So this is where you have a constant factor and amplifier. So you have a constant factor, a cutoff, a point, you have a pole, and then here it flattens back out again. You have a 0. So it's 1 pole, 1 0 is what we're looking for. And that's exactly what we have. And you design the poles and the zeros at these frequencies. So now you have a bass booster when you flip the switch on. 6 dBs is a factor of 2. And now you can calculate everything out. Treble boost, just the flip of that. Same idea. So you get the high frequencies. You just design the cutoff points. You design the pole here, or excuse me, 0 here, and pole here. Okay, end of chapter, and we're going to go on to the next chapter, which are Laplace transforms next.